Hello everybody, welcome. We're going to do our second video on normal subgroups. So when you have a normal subgroup H of a larger group G, you can form what's called the quotient group G mod H. And we talked about that briefly last time, but we'll get into more of the details today. So let me recall for you what the definition of a normal subgroup is. A subgroup H of G is a normal subgroup, denoted H is normal in G with this triangle symbol, if for every element little a in G, the left coset, A capital H, is equal to the right coset, capital H A. What this means, as described in this remark here, is that for any element of the left coset, i.e., for any element little a times little h, where little h is in our subgroup, you can also write this as h prime times a, i.e. an element of this right coset, where h prime is some potentially different element of our subgroup H. Okay, so every subgroup of an abelian group is normal, just because if your group's abelian, then a times little h is always equal to little h times a. So we verified this remark in the easiest possible way. I want to give you an example of a subgroup that's normal. We mentioned it last time, but today let's verify it in full. Okay, so our larger group G is going to be S3, the group of the group of permutations of 1, 2, and 3. And then our subgroup H is going to be the alternating group A3, only containing those even permutations. So the identity and these 2 3 cycles are even, but the 3 transpositions are not even permutations. Okay, so this alternating group is going to be normal. We're going to check it. How do we check it? We have to check that for every element of G, every element A of G, we have A times the alternating group is equal to the alternating group times A. So for every element little a in G, the left coset is the same as the right coset. And we go through here and we check that for all 6 elements of S3. We check it for the identity, the 3 cycle 1, 2, 3, the 3 cycle 1, 3, 2, and then the 3 individual transpositions. Okay? So this is easiest to check when the element is in the alternating group. Because if I take every element in the alternating group and multiply it by an element of the alternating group, I get back an element of the alternating subgroup. You know, that's what it means to be a subgroup. When you multiply 2 elements in the subgroup, you get back a 3rd element of the subgroup. So multiplying by the identity on the left is the same as multiplying by the identity on the right. Multiplying by 1, 2, 3 on the left is not the same as multiplying by 1, 2, 3 on the right. But multiplying by 1, 2, 3 on the left still just moves you around inside this subgroup. And same thing for multiplying by 1, 2, 3 on the right. You know, this element 1, 2, 3 is in the alternating group. So the left coset is just the alternating group, as is the right coset. Okay, let's do a more interesting example. We'll do one of these 2 cycles. Let's do this 2 cycle 1, 2. Let's see that the left coset, 1, 2, times the alternating group, is the same as the right coset, the alternating group, times 1, 2. Okay, so what is the left coset? Well, I take my alternating group and I multiply every single element by 1, 2 on the left. And when I do that, 1, 2 times the identity is just 1, 2. 1, 2 times the 3 cycle 1, 2, 3. Well, this maps 1 to 2, which goes back to 1. So 1 just goes to itself. Where does 2 go? 2 goes to 3. And where does 3 go? 3 goes to 1, which then goes to 2. So 3 goes back to 2. So in total, this is just the 2 cycle, 2, 3. You can multiply the 3 cycle 1, 3, 2 by 1, 2 on the left, and you'll get the 2 cycle 1, 3. What is the right coset? Well, I multiply each element in the alternating group by 1, 2 on the right. The identity times 1, 2 on the right gives me 1, 2. What is this 3 cycle 1, 2, 3 times 1, 2 on the right? Well, it sends 1 to 2, which goes to 3. So 1's going to 3. Where does 3 go? 3 goes back to 1. Okay? So 3 is going back to 1. And 2 is going to 1, which is going back to 2. So 2 staying put. So notice that multiplying 1, 2, 3 by 1, 2 on the left was not the same as multiplying 1, 2, 3 by 1, 2 on the right. Okay? These two are not the same. But in total, the two sets are the same. So that's why the left coset is the same as the right coset here. We just multiplied everything out, and we verified that we got two sets with exactly the same elements. Okay, the same thing happens for these other 2 cycles that you could try multiplying by on the left and the right. You can check by hand that the left coset is always the same as the right coset here. And that's why this alternating group is a normal subgroup of the symmetric group on the set of size 3. Okay. We saw last time, however, that this subgroup containing only the identity and this 2 cycle 1, 2 was not a normal subgroup, since, for example, take the element 2, 3, its left coset was not equal to its right coset. So not every subgroup is normal, but even in non-abelian groups, such as S3, you can still have normal subgroups. So in dihedral groups, symmetries of polygons, such as symmetries of a hexagon, any subgroup consisting only of rotations is definitely going to be normal. The way you prove this is, let's say you have a rotation. So this is some, this is some little h, okay? Well, if you take a flip as your little a, and you consider what is the flip times a rotation, it turns out there's an identity that doing a rotation and then a flip is the same as doing a flip and then the inverse rotation. Okay, you can try this out. So doing a rotation and then a flip is the same as doing a flip and then an inverse rotation. So we have something here of the form a little h is equal to h prime a. Remember that? This is my a little h is written as h prime a. So a, this flip, is an element of my group. R, this rotation, is an element of my subgroup, consisting of some of the rotations. And if R is in the subgroup, then so is its inverse. So I've written a h as some other h prime times a. This also works if for my element little a in the group, I took a rotation just because rotations commute. So there, we'd have AH is equal to HA, where both A and H are rotations. Let's get more specific. So let's work in the dihedral group D4, and let's consider the subgroup of all rotations of D4. So I can take my square, and I can rotate it by 0, or 90, or 180, or 270 degrees. Okay, so this subgroup of rotations I claim is normal. How do we check that? We go through every element of D4, and we check that the left coset of that element is the same as the right coset. Okay, that's easiest to check on the rotations, because the rotations are all in the subgroup, And if you're in the subgroup, the coset, your coset is just the subgroup. So the left coset by R naught is the subgroup itself, which is the same as the right coset by R naught. I should say I'm using rot for the name of the subgroup. This is the subgroup of rotations. Okay, but that works for any rotation. This left coset by R270, well, R270 is one of these rotations in the subgroup. So that's just the subgroup itself. And same thing with the right coset. Okay. What is this coset, the left coset, where I first do where I have a horizontal flip on the left? I guess that's doing the horizontal flip second. Okay. Well, it's take the original subgroup of rotation, so R0, R90, R180, and R270, and multiply them by this horizontal flip on the left. You can go through and check all these multiplications. These give you a horizontal flip, a diagonal flip, a vertical flip, and the other diagonal flip. Same thing if I multiply this subgroup of rotations by a horizontal flip on the right side. So now I'm doing the horizontal flip first. Okay, when I multiply by the horizontal flip on the right side, I get the horizontal flip, one diagonal flip, vertical flip, the other diagonal flip. Okay, these are the same sets, just in different orders. The elements are just listed in different orders. And so my left coset here is the same as my right coset. And you can check that for the other flips, for the vertical flip, the diagonal flip, and the other diagonal flip, showing that this group of rotations is normal. Okay. So let me remind you what the quotient group is. Pretend G is a group and H is a normal subgroup of G. Then the set of cosets of H, the set of things of the form AH, this is a group under the following operation. Two cosets multiply just by taking their representatives, multiplying their representatives, and considering this new coset here. So the coset AH multiplied by the coset BH is the coset ABH. And you should think of this as in some sense you're forming the group by taking G and modding out by H. Okay, let's do two examples. So pretend G is the group of integers 0 up through 11 under addition mod 12. And its subgroup H is generated by 4. So you get 4 and 8 and 12, which is 0. So the elements of G mod H are the left cosets of H. 0 plus H, 1 plus H, 2 plus H, 3 plus H. Here are these cosets. Why didn't I write down the coset 4 plus H? Well, that's the same as the coset 0 plus H. And I didn't write down the coset 5 plus H, because that's the same as the coset 1 plus H. The Cayley table for G mod H is as follows. I have as elements 0 plus H, 1 plus H, 2 plus H, and 3 plus H. To combine two elements, so for example, how do I combine 2 plus H and 3 plus H? Well, this is my AH and BH. And I combine them by taking their representatives, 2 and 3, combining those to get 5, which mod 4 is 1. And so my cosets 2 plus H and 3 plus H combine to give me the coset 2 plus 3 plus H, which is just 1 plus H. Similarly, 1 plus 2 is 3, so the coset 1 plus H combined with the coset 2 plus H gives me the coset 3 plus H. Unsurprisingly, I started with a group of size 12, I modded out by a group of size 3, and what was I left with? A group of size 4. This group of size 4 is actually the isomorphic to the group of integers mod 4. You can see these diagonal stripes as we expect in a group isomorphic to the integers mod n. One final example, G is the group of symmetries of the square. K is the subgroup not of all rotations, but only of the rotation by 0 degrees and the rotation by 180 degrees. Okay? We proved that if you have a subgroup of any collection of rotations, then it's normal up above. So what is the quotient group? The elements of the quotient group are the cosets of K. So you have K itself. Turns out you have R90K as a coset, you have HK as a coset, and you have DK as a coset, where D is one of these diagonal flips. D4 is a group of size 8, right? 4 rotations, 4 flips. K is a group of size 2. So we expect the quotient group D4 mod K to have size 8 divided by 2, or 4. And it does. Here's what its Cayley table looks like. So let's try, multiplying out to get this element to the Cayley table. So what is the coset HK combined with the coset R90K? Well, to get that, I just say, what's H times R90? And H times R90, if I do this horizontal flip and then this rotation by 90 degrees. Let me try this again. Okay. All right, reset. Where do we have A? We have A is closest to my face. Okay, so I do a horizontal flip and then a rotation by 90. That's the same as starting with the same picture and flipping around along, oh my gosh, flipping along this diagonal. Okay, so doing a horizontal flip and then a rotation by 90 is the same thing as instead just doing this rotation along the diagonal. All right, so since H times R90 is this flip along the diagonal, that's why this coset HK combined with R90K is this coset, which is the diagonal flip times K. This quotient group, again, has size 4, but it's not the integers mod 4. This is the Klein 4 group. You can see we have a checkerboard of black and red, checkerboard of black and red, checkerboard of blue and green, checkerboard of blue and green. We don't have these diagonal stripes, right? These diagonal rows are not all the same color. So this is not Z mod 4. This is the group of size 4, which is the Klein 4 group. One reason, and a big reason, why we care about quotient groups is because quotient groups are simpler groups that exhibit some of the properties of the larger group. Here's D4. Here's the Cayley table for D4. D4 has 4 rotations and 4 flips. Okay, we know that it has a quotient group, D4 mod K, that looks like Z2 cross Z2. You can see the structure of Z2 cross Z2 inside this larger Cayley table if you group things together. So on this vertical axis, I've grouped things up together in their cosets depending on K. So K is the coset that has rotation by 0 and 180. R90K is this coset that has the other 2 rotations. HK is this coset that has the horizontal and vertical flip, right here, HK. DK is this coset that has the 2 diagonal flips, right here, okay? And you'll see that the colors that we saw in this Klein 4 group are sort of inherited down here, right? We have a black and red checkerboard, just like we have a black and red checkerboard. we have a blue and green checkerboard, just like we have a blue and green checkerboard. Okay, now things are of larger size because I'm looking at the entire group instead of the quotient group. But, you know, the structure of this quotient group, Z mod 2Z, is living in some form in this quotient, in the structure of this larger group. And so a great way to study big groups that are too large for you to understand all at once is to consider their smaller quotient groups and understand their structures. Okay, so let me end with one last comment. The beginning of this video was talking about normal groups. What does it mean for a subgroup H of a group G to be normal? The second part of this video was talking about quotient groups. How do you take one group and quotient out by a subgroup, and what's the group operation there? What's the connection between normal groups and quotient groups? Well, the connection is you can only define a quotient group when you're quotienting out by a normal subgroup. If your subgroup's not normal, then you can't define this quotient group. So we saw a little of why that was the case in the last video, and we can talk about it during the live portion in class upcoming this week if you'd like. So thanks for your attention.